All right, linear approximations and differentials. Okay, we're going to start off with linear approximations. Let's see if I can keep that off my screen from now on. So we've seen where the tangent line lies very close to the curve at the point of tangency. And if we were to zoom in on a graphing calculator, these two lines would actually be almost indistinguishable from each other. So that's kind of the idea of finding approximate values based off of a tangent line, which is all a linear approximation is. So the reason we want to do that is because it might be easier to evaluate a value off that tangent line than it would be on the actual curve. And so just, you can tell that we have the blue curve and we have the red tangent line. And so the idea of what I just said a while ago was that if I was to actually zoom into even this box right here, the two lines are so similar that we could maybe more easily find something that's on this red tangent line than I could the blue curve. So let's get our idea with this. An equation of the tangent line is going to be y equals f of a plus f prime of a times x minus a. This is, it's a really bad minus a. This is just a rearranged point slope form that we've been using in class. All I did was just move the y1 minus, or I'm sorry, y minus y1. This is my y1 that I just moved over, equals my m times x minus my x1, where x1 is equal to a. And so the approximation of this for my f of x curve is simply going to be this same idea. And it's called a linear approximation. So anytime it asks for a linear approximation, we're just going to be plugging into this formula. Even if it doesn't ask about a linear approximation, but rather it's asking about just the linearization, just the formula in general, it's still going to be f of a plus f prime of a times x minus a. So if you haven't figured it out yet, that's what you want to have really big up in your margin on your practice problems so that you don't forget it. Okay? And I'll get you through about half the homework. So let's see how this is useful. What I want to do is I want to find the linearization of this function at a equals 1. Just imagine plugging in 1 right here. Okay? So if I plug in 1, it just gives me the square root of 4. We know it's going to be 2. Okay? So how is this useful? Well, if I draw my square root of x plus 3, let's see, that's going to send me backwards, 1, 2, 3, I get this curve. So we're saying that a equals 1, we're interested in what that function value might be. And so it might be easier to just find it off of this tangent line instead. Since everything that would be in this box would be very close anyway, I can just work off of it. That's the geometric idea behind it. That's what it looks like graphically. And so let's look and see what it looks like whenever we do this actually using some calculus. Okay, so my f of x is going to be just what they told me. I'm going to go ahead and write it as x plus 3 to the 1/2 because I'm going to end up doing a chain rule on it. So my f prime of x is going to be 1/2 x plus 3 to the negative 1/2. And if I want to rewrite that, so I like to rewrite it so that I get something a little bit easier to plug into. There we go. Now we're interested whenever this thing is at a equals 1. So we're going to need an f of 1. Well, we already said that was 2. And we're going to need an f prime of 1. So if I plug in 1 right here, that's going to give me 1/4. So my linearization is going to be the f of 1 plus the f prime of 1 times x minus 1. Well, f of 1 we said was 2. F prime of 1 we are saying is 1/4 times x minus 1. So altogether that's going to give me 1/4 x, let's see, negative 1/4 plus 2, that should be right around 7/4. So what we're getting at on this is that the square root of x plus 3 can, if I was to kind of straighten this out at the point a equals 1, it should follow pretty closely to this linear line. And so now what I'm going to do is I want to use this to see if I'm getting overestimates or underestimates. So I'm going to go ahead and calculate the square root of, what's the first one, 3.98. And so that's going to be, now this, whatever I'm plugging in for this x right here is going to be close to 1. Okay, as you can see, it's going to be 1/4, and whatever is getting added to 3 here would just be 0.98 plus 7/4. So obviously that turns into a calculator problem. 1.995 would be a 3 decimal approximation on that. Let me explain that again instead of having you work it. So if I'm doing 4.05, what would be my x that I plug in? My x is just going to be whatever I'm adding to 3 that's underneath this square root. In this case, it has to be 1.05, giving me a decimal approximation of 2.0125. So those are my decimal approximations of these two numbers. Are they exact? No, because these two values I found, the 1.995, 2.0125, actually lie on this blue line instead of the red one. Well, looking at that, if I'm picking something that lies on the blue line instead of the red one, is that going to be an overestimate or an underestimate? It's got to be an overestimate because my tangent line lies on top of the curve that was given. So that's the idea of a linear approximation. Okay? I plugged in some more values here. And as you can see, what I would get from my linear approximation right here in this column, it mimics very closely to what the actual value is from my calculator if I was just to keep going with it. Okay? But as you can see, down here, I start getting a little bit further off from it, right? I actually got exactly 2.5 right there, and it was supposed to be 2.449. I'd actually round down to 2.4. So as I get further and further away from this idea of x equals 1, as you can see, x equals 1, I hit it right on right there. As I get further and further away from x equals 1, my approximation gets worse and worse. So what I want to do is I want to know how good is this approximation? How far away can I get using this approximation right here of this curve and still be within half a point of accuracy? I'm just going to warn you, I'm probably not going to do this 1/10 of a point of accuracy. So in other words, if I was to take what the actual value is and subtract off, I'll just use their notation. You can tell that they kind of rearranged some of my numbers a little bit. If I was to subtract off my linear approximation, I'm wondering how long that value stays within 0.5. I guess I need an absolute value on there to make sure if it's negative, I'm still good. So to get rid of the absolute value, what I'm going to do is I'm going to do negative 0.5. It's strictly less than. have this x plus 3 minus 7/4 plus x over 4 is less than 0.5. Got rid of my absolute value in that step. And I'm wanting to isolate my linearization here in the middle. So I'm going to subtract the square root of x plus 3 from each side. I still got that negative in front. I'm going to take care of it on this next step. So I subtracted the square root of x plus 3 from all three parts of this. Now if I divide everything by -1, yeah, that'll work. I did it different in my notes. If I divide everything by -1, that's going to give me positive square root of x plus 3, positive 0.5, and it's going to turn around my inequalities because I'm multiplying or dividing by a negative. Okay. So now I'm going to go make use of my graphing calculator. I don't have it set up just yet, so I'm going to hit pause on my video while I do that. If there's a weird glitch in it, that is going to be why. So let me get everything set up, and then I'll come back and get you guys. All right, I think I'm ready to pick you guys back up. So what I did was I put all three parts of that inequality into y1, y2, and y3. Now something else I should have done was I should have checked my graph to make sure it's all in the right spot. Ooh. I've got a negative floating somewhere. Did you guys see it? Minus 0.5. It should have been on that first one. What happened there? Did I hit a negative on it? I think I used a negative instead of a minus key. What's the chances? What's the chances? All right. Well, you guys lucked out. You're not going to get me to redo this. All right. So it's graphing them in order. I graphed y1 in the blue, y2, my linearization in the red, and the black right there is going to be my y3. Okay. And so how do I know how long this this linearization is going to be good? Well, it's going to be good as long as that linearization line, that red line, is between the black and the blue lines. I'm sorry, the sun has come out and it's just wreaking havoc on my screen. Right. So what does that mean for us? Well, what we're going to do now is we're going to need to find where that red line is in between them at. And so to do this, I'm going to be using my calc feature, second calc, and I'm just wanting to find where they intersect at. Now, the blue line's not really much help on this. The blue line, it doesn't ever intersect the red line. So what I'm going to do is I'm going to go to my first curve, and as you can see, everything turned black right there. I can do black, or I can do blue, or I can do red. I'll do the red, doesn't matter. Second curve is on the black, and what it's going to do is it's going to find the closest spot that it can as to where it intersects. And so that intersection is going to be at -2.65. Okay, remember that for just a second. So I'm going to go in and I'm going to do second calc, and I'm going to do the other intersect as well. So I'm going to send my cursor on down over here to where they intersect again. And first line and second line doesn't matter as long as you're on black and as long as you're on red. There's red. Hit enter again, and I get the 8.657 or whatever that is right there. All right. And so that would be the answers to my questions. So if I'm looking at solving this for x, as long as x is between, let's see what I say, 8.657 and x is between negative 2 point, I think it's like 657, then I'm going to be within half a point of the actual curve. I'm going to meet the criteria of it. Now, if I was to do the second part and I was to use 0.1, I would expect all of my margins to go down. I would expect this range of numbers to get a lot more narrow because the space between my two curves wouldn't be nearly as much. So use a little graphing calculator there to help us out, help us find out what we're doing with that one. Okay. Now I want to touch on differentials as well. Differentials, it can be used a lot in the same way that we did linearizations. However, I have more students that like to use differentials than they do linearization. So the idea behind a differential, you can see it's very similar to a linear approximation, but if we're using y equals f of x, and make sure f is a differentiable function, then the differential, which is denoted just by the dx, is the independent variable. And so that means that d of x can be given the value of any real number. So the differential dy that we're going to be looking for is going to be defined in terms of dx, giving us a nice simple equation of dy equals f prime of x times dx. Not too hard to see where that comes from. dy over dx equals f prime. So if I just multiply both sides by dx, we're good. So let me draw you a picture as to what's going on. Let me attempt to draw a picture. I might have to use my editing software on this. But suppose that I have XY graph, and I'm going to draw a curve like we had earlier. Okay. And then if I have a tangent line to the curve, maybe Christmas is coming up, I'll use Christmas colors. Maybe I can move that dot. Think I can move the dot? Oh, no. I'll move the dot. Pretty close right there. I'll take it. And so where this dot is, I'm going to call that point P right there. Okay. Actually, that's going to be an X. This point P is going to be up here. Now, I'm going to choose a random point that lies on this line right here. I'm going to go way up so you can kind of see the difference of them. Okay. And so the difference between here and where I landed is going to be my delta x. And you know, with delta x, we want to make delta x as small as possible. That was the whole idea with limiting values. But in this case, my delta x and dx are going to be the same. So this value right here has to be x plus whatever my delta x is. Now, we're looking to approximate the dy, the difference, let me use red, the difference just in from this point up to here, okay? That's going to be my delta y. However, using calculus, I can do this distance right here and get a dy since I'm using a tangent line. And so my goal is that as this r slides further and further down, my dy and my dx get closer and closer in value. Okay, so if my r is right here, dy and not dy and dx, but dy and delta y are going to take on a very similar value. I just put it up here so you can kind of see the difference on it. All right, if that didn't make sense, we'll plug it into this equation and see if that will. Get this off the screen. Who brought that back? So I'm going to be comparing the values of dy and delta y. So it told me a y, and then it's telling me a delta x, changing from 2 to 2.05. I might let you try the 2 to 2.01. Okay. So first up, I'm going to need an f of 2 on this. My f of 2 is just going to be whatever I get whenever I plug in 2 in for all these x's. So my f of 2 is going to be 9. Okay. And I'm going to eventually need an f of 2.05. It's going to help me get my delta y here. And so if I plugged in a 2.05 in for all those x's, I got 9.717625. So to calculate what my delta y is going to be is just going to be this 9.717625, what I got for f of 2.05, subtracted off f of 2, and that gives me just that decimal, 717,625. So let's talk about the differential here. So my goal is to get something close to that. My differential dy is going to just be f prime of x dx. Well, f prime of x is going to be 3x squared plus 2x minus 2 times dx. Okay, and what we're interested in is whenever x was equal to 2. Okay, when x is equal to 2, my dy, let's see, I'll put a little x equals 2 here so you can see when I plugged it in, is going to be, look something like this. And then my delta x would be, if I'm going from 2 to 2.05, it would just be 0.05, because that's the difference in my x values. So if I multiply all that by 0.05, it came out to gave me 0.7. That's pretty close. The fact that I got this to be close to the actual delta y, that's pretty good. And that's the whole idea with the differential, is that they're mapping up pretty close. So I'm going to let you, I've done a lot of the work for you, but I'm going to let you go from 2 to 2.01 on your own. Okay, so go ahead and hit pause, and then we'll see what your answer is and what mine is. So I used a lot of the same numbers there, but hopefully you see as my delta x gets smaller and smaller, I was able to match more decimals this time. Oops. I was able to match more decimals this time. And my dy becomes a much better estimation as that gets smaller. All right, one last thing I want to talk about. It's kind of a neat problem here. It looks like we messed it up real bad, but then we bring it back and we're fine. So it's talking about the radius of the sphere as measured, and it found to be 21 centimeters, but we have a possible error in our measurement of at most 0.05 centimeters. So what is the maximum area in using this value of the radius to compute the volume of the sphere? So if my radius is in fact off by 0.05 of a centimeter, how much is that going to throw off my volume? Well, we need the volume of the sphere. Your math teacher still hasn't been able to derive this. Maybe it's coming in a later video. So in this case, what you need to know is that the difference in R, delta R, is going to be denoted by dr. Those are going to be the same thing. So I'm going to use some calculus to help me out here. If I take the derivative of volume, let's get 3 drops down in front, lower the exponent by 1, I've got dr. Now let's talk about what we know. dv is what I'm looking for. My radius was found to be 21, but the error in my radius could have been 0.05 of a centimeter. So that means that my area, you can check me on this one, sorry, my volume could be off by 277 centimeters cubed. that seems like a lot. So let me, it feels like we've messed up. How can it only be off by, the radius only be off by 5/100ths of a centimeter, but yet suddenly my volume's off by 277 centimeters cubed? Well, let's go to, let's redo the, our error, and let's find the relative error. It says to find the relative error, what we're going to do is we divide the error by the total volume, okay? So my error on this one would be my change in volume because of my mistake. Well, I don't have that, so I'm going to be able to estimate it pretty well, though, with my dV that I found. And remember that we said that dV was going to be 4 pi r squared dr. Now, I'm working this kind of the long way. I definitely could have taken my 277 and plugged it in up here, and then went back and plugged in 21 in for my regular volume, and that would give me the right answer. I might still do that. I don't know. So if I simplify all this, the 4's cancel, the pi's cancel, 2 of the r's cancel, and I still have a dr, and that 3 can come up to the top. I get 3 dr over r, which would be 3. My dr was my radius being off by 5/100ths, and then my radius was 21. Less than 1% on that relative error. So not bad when you consider that. That's it. You can check Google Classroom for your homework. Make sure it's, I don't want to click the next slide like I have been doing in case it has changed. So if you have any questions, make sure you let me know, and I will catch up with you guys next time.